Okay, we're going to walk through the solutions to the 1B practice. Explain why n and n plus 2 can be used to represent a pair of consecutive odd integers, as well as a pair of consecutive even integers. So, we need to take a look at some consecutive odd integers. So for example, if we start with 3, the next is 5, 7, 9, 11, etc. And then let's also take a look at some consecutive even integers. So for instance, if we start with the number 6, the next is 8, the next is 10, the next is 12, etc. And so what you'll notice about these lists is that each list, the next consecutive integer, whether odd or even, is formed by adding 2 to the previous one. So regardless of odd or even, consecutive odd and consecutive even integers always differ by 2. So what that means is, if you have a smaller one, the difference is 2, you can add that difference to get the next integer. All right, in 2 through 7, we are going to use the variable that's defined for us and write an equation to represent the situation and not solve. In number 2, we have 2 consecutive integers. N is defined as the smaller integer, so my first integer, or the smaller one, is equal to n. My second integer, or the larger one, is n plus 2. Now we're going to translate each part of this sentence one by one. So let's take a look at what it says about these. 5 less than 3 times the smaller integer. So let's take a look at that phrase right there. 3 times the smaller integer would be 3 times n. 5 less than that means we subtract 5 from that. The word is our equal sign in mathematics when we translate from English. Now let's look at the remaining part of the phrase, double the value of the larger integer. So double means 2 times that, and the larger integer is n plus 2. We need our parentheses there because we have to find the value of the larger integer by adding 2 before we can multiply it. All right, let's take a look at number 3. The product of 2 consecutive odd integers is 35. So I'm going to let my n be my smaller integer, or my smaller odd number, and then n plus 2 is my larger odd. And we have this word here, product. Product means the result of a multiplication. So we need to multiply n times n plus 2. And again, we need to figure out what the value of that larger integer is. That's why we have those parentheses there, so that we can add 2 to figure out what that value is before we multiply it by n. Is 35 equals 35. So the product of those 2 integers equals 35. In 4, we have a right triangle, and so I'm going to draw a picture to represent our variables. And the side lengths of this right triangle are described here. So it says that the longer leg is 2 inches more than double the shorter leg. X is the length of the shorter leg, and so the longer is 2 inches more than double the shorter leg. So that would be double the shorter leg plus an extra 2. And then the hypotenuse is 3 inches longer than double the shorter leg. So double the shorter leg plus 3. What we know about sides in a right triangle from geometry is that a squared plus b squared is equal to c squared. The important thing there about the Pythagorean theorem is that c is the hypotenuse, and we know the hypotenuse is always opposite the 90-degree angle. So a can be x, b can be 2x plus 2, but again, we need to figure out the value of 2x plus 2 before we can square it. And then on the right side, 2x plus 3 squared. If those parentheses are not there, it changes the meaning of your equation. And so if you have doubts about those parentheses, we can talk more about that at another time. In number 5, we have a distance, rate, and time problem. So I'm going to set up a chart to organize the information. There are 2 runners. So I will label the first runner 1 and the second row runner 2. And I'm going to write the units of the rate, which are miles per hour. The fraction here suggests that we multiply by hours, and that'll give us a result of miles. So, first runner runs at a rate of 6 miles per hour, and the second at 10 miles per hour. Let t equal the number of hours it takes the second runner, so runner 2, to catch up with the first one. Now, runner 1 and runner 2 start at the same time, so that means that both of their times, the amount of time they're going to be running, will be equal to one another. And if we take the information in the chart now and multiply as suggested by the formula above the chart, miles per hour times hours gives us the miles, then 6 times t is how we figure out the miles. For runner 1, runner 2's miles are determined by 10 times t. Now we need a diagram. So runner 1 starts and runs at a rate of 6 miles per hour. Runner 2 was not given the same head start, so they're starting further back and run, and at the point where runner 2 catches up with the other, they're going to be neck and neck. So they're going to be at this end point there where the arrows are indicated. Runner 1's time is 6t, runner 2's time is 10t, and the thing that we're missing here is that head start. That head start was 1 mile. Now we have an equation that's suggested by that diagram. Part plus part is equal to whole, so 1 plus 6t is equal to 10t. Now moving on to problem 6. It takes 40 minutes longer to drive from Abbott to Benson at 30 miles an hour than it does to return at 35 miles an hour. Let t equal the number of hours the return trip takes. So I'm going to make my chart again for organizational purposes, and our rates are measured in miles per hour. I'll write that in fraction form. Suggest that we should be multiplying that by the number of hours to get a result that's measured in miles. And we have the trip from A to B, or Abbott to Benson, and then returning, that would be Benson to Abbott. And it says that t is the number of hours that the return trip takes. So t is going to go here in the number of hours for Benson to Abbott. What we also know is that it takes 40 minutes longer to go from Abbott to Benson than it does to return. So there are more hours in the going trip. However, 40 minutes needs to be changed to a fraction, and that's 2/3 of an hour. Our rate for Abbott to Benson is 30 miles per hour, and then our rate coming back is 35 miles an hour, which is why it takes less time. And miles per hour times the hours gives us each of the distances. And if this is Abbott and this is Benson, our trip from Abbott to Benson the distance is 3 times t plus 2/3, and the trip from Benson back to Abbott, the number of miles is 35 times t. We can see that the two distances have to be equal because Abbott and Benson aren't moving. So we set those equal, and now we have the equation that represents the situation. In 7, we have Alan and Dave leaving from the same point, driving in opposite directions. Alan at 55 miles per hour, Dave at 65. Dave left 1 hour after Alan. So again, I'll set up a chart to organize the information. Miles per hour, those are the units of the rate, and we need to multiply that by number of hours to get a result measured in miles. And our two players here are Alan and Dave. All right, Alan drove at 55 miles per hour and Dave at 65 miles per hour. The t, pay attention to this, is the number of hours that Dave had traveled. So t will be Dave's number of hours. Now Alan left earlier, right? Dave left 1 hour after Alan, so that means Alan was on the road earlier, which means Alan had 1 more hour to travel. Person who left earlier has more time to travel. Alan's time times his miles per hour is equal to the number of miles, and same for Dave. The rate times the time is equal to the distance. And they leave from the same point, traveling in opposite directions. So Alan's distance and Dave's distance, and we are looking for that number of hours, or we're letting t equal the number of hours that have elapsed when they eventually are 255 miles per hour. Well, that suggests part plus part is equal to whole. So the two smaller distances added up are equal to the larger distance. And there's our equation. All right, in 8 through 11, we are actually defining our own variable and then using it to write an equation and solve to answer each question. So in 8, we have 1 less than 4/7 of a number is the same as half the sum of the number, and 3, find the number. So let's let x equal the number. Let's take this first expression before the word is. 1 less than 4/7 of a number. 4/7 of a number is 4/7 times the number, so that would be 4/7 x. 1 less than it means we subtract 1 from that expression. Is translates to the equal sign, or is the same as is also another way to say that. And the part on the right side of the equal sign will be half the sum of the number and 3. Well, in order to take half of a sum, you have to do that addition first. So the sum of the number and 3 would be x plus 3. We'll put that in parentheses, and then we're going to multiply that by 1/2. Half of the sum is half of that quantity. Once we get to that point, we actually need to solve this one. So I'm going to take and multiply both sides of the equation by the least common denominator, which is 14. So 14 over 1 times 4/7 x minus, and we need to distribute that multiplication times 14 to both of the terms in the subtraction on the left side of the equation. And then on the right side, I'm just going to write that 14 over 1 times 1/2 times x plus 3, and we haven't actually done those multiplications yet. All right, on our left side of the equation, we can do some canceling here. 14 divided by 7 is 2. That's going to give us 8x is the result of that multiplication. 14 times 1 is 14. And then on the right side of the equal sign, we can also do some canceling here. we can cancel 14 divided by 2 is 7. And so that's going to give us 7 times x plus 3, which is 7x plus 21. Once we get to that point, subtract 7x off from both sides, and then add 14, and that gives us x is equal to 35. And so the number was what x represented is 35. And sometimes when we solve for x, we don't get the answer to the question. In this case, we did, since x represented what we're trying to find. All right, let's check out this one. Find the measure of the largest angle in the triangle below. Note this figure is not drawn to scale. So what we know about angles in a triangle is that each of the angles has to add up to 180 degrees, or all three angles, I should say, have to add up to 180 degrees. Well, since we're going to solve this one, we actually don't need those degree symbols. Let's just pretend those degree symbols are not there. In general, we don't have to put units in our equations, and sometimes it actually gets in the way if we do. So we're just going to combine some like terms. 5x plus 2x plus 3x is 10x. 30 and 40 are 70, and that equals 180. Subtract 70 from both sides, and then divide by 10, and we'll get x is equal to 11. Now that is not the answer to the question, because x is not one of the angles. If x is 11, then 5 times x is 55 degrees. If x is 11, 2 times x is 22 degrees, plus 30 is 52 degrees. And then if x is 11, 3x is 33 degrees, plus 40 is 73 degrees. And so what is the measure of the largest angle? That would be 73 degrees. Now, as a check, we can just check that 73 plus 52 plus 55 add up to 180 degrees, and in fact they do. In 10, we have a triangle, we have a quadrilateral, and its perimeter is 26 inches. What is the length of the shortest side? Well, this may or may not be a square, right? It looks like a square, but it's just described as a quadrilateral, so we have no idea if any of these sides have equal lengths. What we do know is that the perimeter is the sum of all the sides. So 1/5 x minus 2 plus x plus 2 plus 2.5x minus 10 plus x has to equal the 26-inch perimeter. Notice I didn't write inches there. That's just going to get in the way. Now we need to add together our like terms. We have 1.5x plus 1x plus 2.5x plus another 1x. So 1.5 plus 2.5 is 4 plus x is 6x. And then we have also like terms minus 2 plus 2 and minus 10. So that gives us a total of minus 10 equals 26. And adding 10 to both sides, 6x equals 36, or 6 times x equals 36. Dividing by 6, x is equal to 6. Now we're going to go back and find the length of each of the sides. So x is 6. 1.5 times x. Well, a half of x is 3, so 1.5 times x is 9, minus 2 is 7. X plus 2 will be 6 plus 2 is 8. 2.5 times x. Well, 2 times 6 is 12, and a half times 6 is 3. So 2.5 times 6 is 15, minus 10 is 5. And so what is our shortest side? So our shortest side is 5. And it would be a good idea to put units on that, 5 inches. All right, in number 11, the sum of three consecutive integers, consecutive odd integers, look for that word right there, is 9 more than double the greatest of the three. Find the three integers. Well, our three integers are going to be n plus 2, and n plus 4. Since they're consecutive odd integers, they differ by 2. The sum of those consecutive integers is what I get when I add them together. So that will be n plus 2 plus n plus 4. Then we find the word is. And on the other side of is, we have 9 more than double the greatest of the three. So double the greatest one is 2 times n plus 4, and then add 9 to that. Parentheses necessary here because we need to figure out what n plus 4 is equal to before we can double it. So that's just indicating that that operation has to go first. All right, on the left side of the equal sign, 3n plus 6. On the right side, we actually can get around the parentheses by using the distributive property of multiplication over addition. That is only valid if we're multiplying and we're distributing the multiplying over addition or subtraction. There are some other distributive properties, but we can't distribute whatever operation we want to. All right, 3n plus 6 is equal to 2n plus 17. Subtract 2n from both sides, and now subtract 6 from both sides, and we get n is equal to 11. So it looks like our three integers are 11 is the smallest, 13 is the next largest, and 15 is the largest of the three. In the last exercises here, we're going to organize the information to find a variable, then write an equation. And these are distance, rate, and time problems, so we're going to organize our information using a chart. Your time answers, when we give units on those, should be expressed using hours and minutes. And what that means is we're going to express all of our answers in hours using fractions when necessary. And we use improper fractions, remember, in algebra. All right, Jenny had driven for 3 hours at constant speed when road repairs forced her to reduce her speed by 10 miles per hour for the remaining 2 hours of the 250-mile road trip. Find her original speed. All right, I'm going to get organized here. These rates are measured in miles per hour, which I'm going to write in fraction form. That suggests that we should be multiplying by hours and get a result measured in miles. And Jenny was driving for the first part of her trip and for the second part of her trip. We're not told what her speed is, but the first part of the trip is 3 hours and the second part is 2 hours. We do know that road repairs forced her to reduce her speed by 10 miles per hour for the second part. So if we're looking for her original speed, I can make that r. That would be for the first part of the trip. For the second part, r minus 10, since it's reduced by 10 miles per hour. Now, if you wanted to set this problem up where the second part was represented by r and the first by r plus 10, you absolutely could. Multiply to find the number of miles, and then let's draw Jenny's trip. Here's the first part of her trip. She went a distance of 3r, and then continuing from the same point, she went a distance of 2 times r minus 10. And what we do know is that the entire trip was 250 miles. That suggests that 3r plus 2 times r minus 10 is equal to 250. Let's use the distributive property of multiplication over subtraction. Combine like terms. And then, oops. Sorry, I made a boo-boo there. And then add 20 to both sides. And then we've got to divide 5 into 270. Let's do that right here. 5 divided into 270 goes 5 times into 27. That gives us 25 with 2 leftovers, 54. So we're looking for her original speed, and fortunately for us, we've used a variable that represents the original speed. So we've actually found the original speed, which would be 54, and that you can see from the chart is measured in miles per hour. You can use mph if you like. In 13, at noon, a private plane left Austin for Los Angeles at 500 kilometers per hour. 1 hour later, a jet left Los Angeles for Austin at 700. At what time did they pass each other in the sky? Okay, so we have our plane and we have our jet, and the rates this time are measured in kilometers per hour. So we're going to multiply by hours and get a result that's measured in kilometers. Our private plane flew at 500 kilometers per hour, and the jet at 700 kilometers per hour. Now, here's the thing. I don't know which one of these times to call t, and the thing is we can use either one. I'm going to choose the private plane, and here's my reasoning. The answer to the question is actually a time, like what o'clock is it? And it will be easier if we use the private plane's time because we're just measuring the time since noon. So the private plane leaves at noon. Let's call that t hours. The jet leaves later. The person who leaves later has less time on the road. The number of kilometers would be 500 times t and 700 times t minus 1. Now let's draw our picture. Here's Austin and here's Los Angeles. The private plane leaves at noon and drives, or rather flies, and at 1 o'clock, 1 hour later, the jet leaves and flies in the opposite direction. When they pass one another, they're meeting kind of in the middle. And the two cities, we are told, are 2,100 miles apart. So our plane's distance is 500 times t, and the jet's 700 times t minus 1. That suggests a part plus part is equal to whole relationship. So those two distances total 2,100. Now let's use the distributive property of multiplication over addition to rewrite the left side. And that'll give us 1,200 t minus 700 is equal to 2,100. And adding 700 to both sides, 1,200t is equal to 2,800. Lots of big numbers here, but they're going to get small pretty quickly here. So t is equal to 2,800 divided by 1,200. And if you've ever heard of striking zeros, that just means reducing your fraction by powers of 10. So divided by 10, divided by 10. Now we have 28 over 12, and that reduces by a factor of 4 to 7 over 3. So 7 over 3, let's re-express as a mixed number. For algebra, an improper fraction is great, but mixed numbers are better when expressing your answers. 3 goes into 7 2 times with 1 left over. So that's 2 1/3 hours. So that's actually 2 hours and 20 minutes. And remember that the question is asking for what time of day. Well, the plane, whose time was t, left at noon, and so that would be 2 hours and 20 minutes after noon, which would be 2 8:20 p.m. All right, let's take a look at 14. At 8 a.m., the Smiths left their campground driving at 48 miles per hour. At 8:20, the Garcias left the same campground and followed the same route, driving at 60. At what time did they pass the Smiths? So, we've got the Smiths and we've got the Garcias, and our rates are measured in miles per hour multiplied by hours equals miles, and Smiths at 48 miles per hour, Garcias at 60. And let's let the time belong to the Smiths. It'll be easier to measure the time relative to the Smiths' departure because they left at 8 o'clock. The Garcias left later, which means that they have less time to drive. They left 20 minutes later. That's 1/3 of an hour, so we're going to convert that to hours. Now our miles are 48 times t and 60 times t minus 1/3. Drawing a picture, here's the campground, the Smiths leaving, and then the Garcias leaving at the same time. When they're passing each other, we can actually see that the two distance is 48t and 60 times t minus 1/3 are equal to one another. So I'm going to set them equal to one another and then go from there. So the two distances, 48t and 60 times t minus 3 are t minus 1/3 are equal. Let's use the distributive property. 48t is equal to 60 times t minus 1/3 of 60 is 20. And now we can subtract 60t from both sides. That will give us negative 12t equal to negative 20, and then dividing by negative 12, a negative divided by a negative is a positive. 20 divided by 12, both of those are reducible by 4, correct? So if we reduce by 4, that'll give us 5/3 of an hour. That's the time since the Smiths left. So 5/3 of an hour is equal to 1 2/3 hours, which is the same as 1 hour and 40 minutes. And the Smiths left at 8 o'clock, so that means that the time when they pass one another is 9:40 a.m. And last one, I believe this is the last one. It took Cindy 2 hours to bike from Abbott to Benson at constant speed. The return trip took only 1 hour and 30 minutes because she increased her speed by 6 kilometers per hour. How far apart are Abbott and Benson? Okay, so again, we'll set up a chart, distance, rate, and time. And our rates are now measured in kilometers per hour. That suggests that we should multiply by hours and get a result measured in kilometers. And we're going from A to B, and then B back to A. So it took Cindy 2 hours. That's something we can put in the chart immediately to go from Abbott to Benson. The return trip took 1 hour and 30 minutes. Well, 1 hour and 30 minutes is 1 1/2. We're going to change that to an improper fraction 3/2 so that we can use that algebraically. What we know is that Cindy's rate going can be called R, but when she returned, she increased her speed by 6. That's why she spent less time. She was going faster. So our number of kilometers are 2R, and 3/2 times R plus 6. And from Abbott to Benson, and then back from Benson to Abbott, are actually the same distance. You may not necessarily need to draw a diagram to see that, but I suggest that you get in the habit of doing that so that if you are wondering what's the relationship, you can see it if you make a picture. So 2 times r is equal to 3/2 times r plus 6. The very first thing I'm going to do to both sides is clear those fractions. So I'll multiply both sides by 2. 2 times 2r equals 2 times 3/2 times r plus 6. All right, on the left side we have 4r. On the right side, 2 over 1 times 3 over 2. Our 2's cancel. Now they're just left with 3. 3 times r plus 6 is 3r plus 18. Subtracting off 3r from both sides, r is equal to 18. Now, what did we just find? R is how fast Cindy was going from Abbott to Benson. We can see that in our chart. R is Cindy's kilometers per hour from Abbott to Benson. That's not what we're asking for, right? They're actually asking us how far apart. That would be measured in kilometers. So how far apart are Abbott and Benson? Well, there's 2 expressions for that distance, but the easiest one to work with is 2 times r. So our distance is 2 times r, which is 2 times 18, and that's going to equal 36, and that would be measured in kilometers. So sometimes when you solve for your variable, it's not what you're looking for. So we have to be conscious of what the variable stands for. That's where our chart really helps us out. That wraps it up.